Hello everyone, I am Mithuna Shri S from Sri Venkateshwara College of Engineering from the Department of Computer Science and Engineering, studying in 5th SEM Bhaskara. Today our subject is Theory of Computation and the topic we are going to discuss is decision problems of finite automata design from a research paper. So let's know some key points of decision problems of a finite automata design. This presentation explores the fundamental decision problems associated with the design of a finite automata, delivering into key concepts and practical application in computer science. So let's know the introduction to finite automata. The finite automata is defined as a mathematical model of computation that consists of a finite number of states and transitions between those states. And applications of it involves it has a numerous applications in computer science including lexical analysis, text processing, and pattern recognition. And types of finite automata can be deterministic or non-deterministic, which is called as DFA or NFA, each with unique properties and capabilities. So next, let's know about deterministic finite automata. Deterministic finite automata is for each state an input symbol. That is, one state has only one input symbol. There is only one transition to another state. The formal definition of DFA is it is a file tuple which is Q, sigma, transition Q naught and F, where Q is set of finite states and sigma is finite input alphabet and transition function, and Q naught is the initial state and F is the final state. The acceptance of DFA is string if and only if the sequence of transition leads to final state after processing the string. So, what is non-deterministic finite automata? From non-deterministic finite automata is from a state multiple transitions can occur on the same input symbol or no transition at all. That is indeterministic we had only one transition from a state, but in non-deterministic it can have multiple transitions. And epsilon transition. NFAs can have transition on empty string, allowing them to change states without consuming an input symbol. And acceptance. An NFA accepts a string if any sequence of transition, including E transition, leads to a final state. Conversion between DFA and NFA. DFA to NFA. Every DFA can be converted into an equivalent NFA by introducing epsilon transition. This process is straightforward. NFA to DFA. Converting NFA to DFA involves construction of new DFA with states that represent set of NFA states. And equivalence. The resulting DFA accepts the same language as the original NFA, demonstrating the equivalence of the two models. Next is minimization of DFA. Motivation. Minimization reduces the size and complexity of a DFA without affecting its language recognition capabilities. An algorithm used for minimization is partitioning states into equivalence classes board and their ability to reach accepting states. Uniqueness. The minimized DFA is unique for each language and represents the most efficient implementation of automation. The next is equivalence and contaminant of regular languages. Equivalence. The two regular languages are equivalent if they accept the same set of strings. This can be checked using DFAs. And contaminant. One regular language is contained in another if all the strings accepted by the first language are also accepted by the second, but all the strings accepted by the second may or may not be accepted by the first language. And decision problems. Determining equivalence and contaminant of regular languages are important decision problems with practical applications. And closure properties of regular language. The closure property. Regular languages are closed under various operations, including union, intersection, concatenation, and clean star. Significance. Closure properties allow us to construct complex regular languages by combining simpler ones through these operations. Implications. Understanding closure properties is essential for designing efficient algorithms for processing and manipulating regular languages. And when we see about future directions, importance is the finite automata are fundamental to computer science with applications in numerous areas. And decision problems. Understanding decision problems for finite automata is crucial for practical applications. And the future research will explore advanced techniques and efficient design, and also many importance of finite automata. And when we see about the conclusion, finite automata are fundamental models of computation that play key role in recognizing patterns and defining regular language. They serve as the foundation for various applications in computer science, including lexical analysis, text searching, and network protocol validation. By simplifying complex problems into logical structures, finite automata provide valuable insights into theoretical computation and real world problem solving. Their relevance extends to more advanced computational models, highlighting their importance in both academic study and practical applications. Understanding finite automata is essential for exploring the broader scope of computation and innovation in computer science. Thank you.